Good afternoon, dear students. Welcome to the Gradeup, the India's largest e-learning platform. Dear students, come on, join this session very fast. Yes, dear students, welcome to the Gradeup once again, and very good afternoon. Yeah, join the session. Today is the marathon session, dear students, that we have planned to complete this entire metal forming along with the sheet metal working. These two topics, the today and tomorrow, right? Today and tomorrow, Tuesday and Wednesday, 2 to 4. So come on, join the session and tell me whether I'm visible and audible to you guys. So this is the topic from the production engineering, dear students. So this is one of the, dear students. See, we are going to target some of the topic in the production engineering. So where definitely we are having the scope, the chance to get out of mark from that particular topic. Say for example, we are having this production. In that production, we are having the forming processes, sheet metal processes, then the metal cutting, right? So these are the some topics, dear students. So from where you will be having the sure short questions, and for that, to get that out of marks from this particular topic, dear students, we are arranging such a kind of sessions. So come on, dear students, join this session very fast and let me know. Vikrant, very good afternoon, dear. Very good afternoon. Yes, come on. Akhilesh, very nice, Akhilesh. Good afternoon, dear. Good afternoon. चलो ज्वाइन करो भैया, जल्दी से ज्वाइन करो, आ जाओ सब लोग. Share this information, dear students, amongst your friends so that everyone get benefited. So yes, come on, join the session. So shall I begin? Shall I begin? Vikrant, Prasad, Akhilesh. So dear students, see. So if you look at the background of this topic, definitely the metal forming, you know what is mean by metal forming? Where the shape and size of the product is obtained by deforming the material plastically. Okay, that is by producing the permanent deformation in the given raw material, we are trying to get the shape and size, required shape and required size of the product. This is nothing but the metal forming, right? So yes, we are going to understand this topic. Yes, come on. Yes, this is about me. This is about me. I am Onkar, having more than 10 years of experience for teaching GATE and ESE. Till now, I have mentored. So PPT is shared to in the below only, dear. In this chat only, we are sending the PDFs. I hope you got the previous PDFs. Akhilesh, Vikrant, what is about you? So my area of expertise are production and industrial engineering, fluid mechanics, mechatronics, robotics as well. So yes, we are going to talk. So shall we directly go for the solving the questions, or some of the background should I discuss in short? So that you will have some revision kind of thing, this particularly about the formulas, the background of the topic metal forming. Okay, so within no time, okay, we will just have the just revision kind of thing for the metal forming, so that we can able to solve the questions, Yes. I know that due to some issues yesterday it could not able to happen. But yes, in future coming 5 to 6 days or within the week, definitely I'm going to plan the same. Okay. Don't worry about this. You attend the sessions. You attend the sessions. Ask your friends to attend the session, dear students. I hope whatever the 5 to 6 sessions till now we have completed at 7 p.m. every day, starting from the casting, welding, then what forming, metal cutting, all the sessions. I hope I have seen the PDFs and these are very helpful to you, right? So these were our 6 to 7 days plan for the crash course. Yes, one is already left, metrology inspection. Definitely it is going to cover. I will definitely cover it within 5 to 6 days, right? Okay, so let us have some little discussion about the metal forming. So as definition you know very well, as definition you know very well, right? And do join this telegram channel, dear students. Vikrant, and who want this, all the PDFs will be available here. Do join this telegram channel, dear. Okay. So yes, let us start about this metal forming. Come to our topic, metal forming. Okay. So every year, dear students, definitely around say maximum, I am telling maximum 4 to 5 marks definitely we are going to get from this particular topic. And again in this particular topic, what is there actually? So little bit, if you look at the background, if you look at the background of this topic, the forming. So definitely now there is a very important discussion is there on the fundamentals of metal forming. Okay, so in fundamentals of metal forming is what? So with the definition, okay, what is metal forming, what are the advantages of metal forming compared to the other processes? Like if you compare the advantages, sir, complete revision of formulae. So yes, so this will be planned in the month of January. So this will be planned in the month of January. So for that we are going to have the revisions of the formulas. Okay, all the formulas, entire production engineering. You just tell me, sir, that we want this particular marathon series session or particular 2 to 3 sessions on particular this topic. Definitely we will think to plan such a sessions, particularly for say forming, then any for metal cutting. You take any topic or you take the formulas also. Entire production engineering we can able to discuss the formulas only also. No any issue for that. You just decide, you just put your thoughts in the chat box so that we can discuss and we can think for particular series or particular sessions. Yes, definitely. Yes, Vamshi, very welcome suggestion. Definitely we are going to plan for that also. But I have to complete the production engineering in the first go, then we'll think for that industrial engineering also. Okay, very nice, Vikrant. Join this telegram channel, dear student. Join this telegram channel, you will get each and everything there. So all the faculties, so whatever the series sessions are there, definitely it will come to you, right? All the material will be available there, so don't worry about that. So see, so fundamentals of metal forming, we didn't particularly talk about what is cold working, what is hot working, what is the difference between cold working and hot working, right? So these are the very fundamental things we talk about. So we also talk about the what is the plastic deformation zone, okay, how that plastic deformation zone can be uh, get widened so that our deformation also get widened, so that we can have more and more working on the material, right? So like this is our PDZ, right? So these are the very basic things we try to learn in the fundamentals of metal forming, where we also see that the Hooke's law is valid say for the strength of material, okay, up to the elastic limit. But in the plastic deformation, definitely when you talk about the metal forming, so there is a law which is valid here, which is known as the power law. because this obeys the power law. This region of plastic deformation zone is going to obey the power law or the Holloman-Ludwig equation, isn't it? So what is that actually? So that also very important, dear students. We know that this true stress is equal to k into epsilon to the power n. This is very important power law, Holloman-Ludwig equation, dear students, right? Yes, everything we will plan, Vikrant. Just respond me in that way. Increase the presence of the students. Okay. So there should be some number, right? If it is there, definitely we will plan each and everything. Share this information. Ask your friends to join. Okay, so you know this equation, dear students, that is a Holloman-Ludwig equation, or this is the power law, or this is also known as the flow curve equation. Flow curve equation. This is valid actually when you talk about the strain hardening region, which is the plastic deformation zone. Actually, strain in the strain hardening region, dear students, the Hooke's law is no more valid. There is a power law, which, or this curve, this is the flow curve equation. Sigma t is equal to k into epsilon to the power n, where you know k is what? The strength coefficient. K is strength coefficient, you know very well. Epsilon is what? The true strain. Okay, and n, very importantly, dear students, n is our strain hardening exponent. So very important. So actually see, this is directly give us, so higher the value of the strain hardening coefficient, harder will be the material. Okay, so definitely n value goes on increases, there is a chances of having the material to get harden and harden when it will undergo deformation. Okay, so yes, so this value particularly for the strain hardening exponent, dear students, for the engineering materials, I am telling you the value is from 0.10 to 0.50 for the structural or engineering materials, whereas for the plastic material it is equal to 0. Perfectly plastic material, very important, dear student. Perfectly plastic material. So if I say perfectly plastic material, it is like this. It is 0, it is linear 1, and it is between, say, n is greater than 0 and less than 1. So like these are the materials. Linear, for for perfectly elastic material, it is 1. Okay, perfectly plastic material, this n is equal to 0. So like that, you just keep it in mind. For this is for engineering or structural materials. So this is the strain hardening exponents. Higher the value of strain hardening exponent, higher will be the hardness, higher will be the strength of that material. K is the strength coefficient. Sigma t is the true stress is equal to K into epsilon to the power n. So based on this equation also, we are getting many questions in the GATE examination. Please, so definitely we are going to solve some very important question based on this particular relation, flow curve relation. Also, they are asking many times what is the work done in the deformation zone, or what is the work done, okay, in the metal working or in the metal forming. So dear students, as you know, suppose up to this I have worked the material causing the strain in the material, say epsilon f, and if I take the small strip of this epsilon, that is say d epsilon, and this is the true stress value. Of course there is a change, but this change I am saying it is very less. This is the sigma t. Then dear students, what is the work done during the deformation? So definition, you know that the work done during the deformation is nothing but the area under this tension curve, you know that. So up to the fracture, so up to the strain which is induced in the material, say epsilon f. So definitely if I try to get this strip here, okay, of width d epsilon and height, say sigma t, and I integrate over this region in this under the stress strain curve, okay, so that will be my work done. And definitely it is per unit of volume. I can write is equal to integral. It is the strain actually from where, actually the strain after the elastic, after this elastic deformation, definitely, but this distance or this strain, elastic strains are very less. So what I am doing, I will directly take the limit from 0 to epsilon f, that is integral 0 to epsilon f. what is there? This sigma t, that is the height, okay, into this d epsilon. Okay, and what is this sigma t? Jay Kumar, good afternoon. Sigma t is what? K epsilon to the power n into d epsilon, integral 0 to epsilon f. So it will be k into, what is the integral of epsilon to the power n d epsilon? X raised to n. It is x raised to n plus 1 divided by n plus 1. So k into epsilon to the power n plus 1 divided by n plus 1. And what are the limits from 0 to epsilon f? It will be what? K epsilon f, put the limit of epsilon f. So k epsilon f to the power n plus 1 divided by n plus 1. Dear students, please remember, this is the work done. This is the work done in the deformation. Okay, in the deformation zone, actually in the plastic, say, because here the elastic deformation is very less. We are just taking it from 0 to epsilon f. So this is the work done in the deformation, which is nothing but, and yes, work done per unit volume. Don't forget, this is the work done per unit volume, because see, this stress strain curve, if you take here, so what is the volume actually? Okay, so this is the stress. Stress is what? Sigma into this epsilon. So this is the area under this curve. What is that? So stress is Newton per mm square. Okay, into strain is what? Change in length, millimeter, divided by original length, mm. So it will be what? Newton mm per mm cube, isn't it? So but I want the work done in terms of the joule. What I can write? So Newton, say, into, so Newton meter, say 1 meter is equal to what? 10 to the power, so minus 3 actually. So 1 millimeter, I have to convert it into meter, definitely into 10 to the power minus 3 meter, divided by this mm cube. If I take into a meter cube, then it will be into 10 to the power minus 9, isn't it? So ultimately what I will get here? I will get here, say, Newton, if I want to write here, Newton meter per this meter cube. See, Newton meter is what? Work done. This meter cube is what? The volume. So this work done per unit volume, this is nothing but our whatever the formula that we have got, this k epsilon f to the power n plus 1 divided by n plus 1. I will get here. So tell me here, 10 to the power minus 9 अगर यहाँ पे आ गया तो क्या होगा? 10 to the power 9 into 10 to the power minus 3. So it will be how much? It is 10 to the power 6. 10 to the power 6 Newton meter divided by meter cube. That will be, see. So 10 to the power 6 is what? It's a mega. It's a mega. Newton meter is what? Joule per meter cube. So that is the unit of this work done here. So what is the unit actually? So whatever the work done we have seen here per unit volume, that has the unit of, don't forget, it is having unit of megajoule per meter cube. Megajoule per meter cube. So this is the work done. Okay, and here, so whatever the work done, if I have, I compare with the some average value of stress, okay, instead of taking the sigma t, I am saying that, say, some flow stress, which is, say, sigma t, or say sigma t average, if I take for particular, for this work done. Okay, what was the work done? K epsilon f to the power n plus 1 divided by n plus 1. So definitely, if I if I equate this work done with some flow stress, okay, average flow stress over this entire plastic deformation zone into the strain, okay, epsilon f, then what will be the flow stress? Tell me, what is the flow stress? So average flow stress will be how much? So k epsilon f to the power n divided by n plus 1. So please remember, so whenever they need to, or we need to calculate this flow stress or average flow stress, okay, flow stress or average flow stress, so it is equal to what? K into, because see, this epsilon f, if I write this epsilon f to the power n plus 1 like this, epsilon f to the power n into epsilon f, so this epsilon f gets cancelled out, and you will get the average flow stress as k into epsilon f to the power n divided by n plus 1. So this is the average flow stress, dear students. This is the average flow stress. Okay, whenever we require, definitely we use this equation. No any issue. So please remember, from the fundamentals of this metal forming, dear students, these information should be known to us. Okay, along with that, the very basic thing about the, say, true stress, true strain, normal stress, nominal stress, or normal strain. So see, the flow stress, you can take it as the true stress only, but when so instead of taking the sigma t at particular point, so I'm just, whatever the work done is there, whatever the work done is there, I have calculated. So it should be equate with some say average value of stress. So see, sigma flow is what? This is the instantaneous value of the stress. Actually, this is the instantaneous value of the stress I have taken. Okay, instead of taking the true stress. Okay, so these are same only, but this is, say, instantaneous value of stress, okay, which is taken at that particular point. Flow stress of the material. Because see, what is mean by flow stress? You know that. So basically, whenever the raw material is subjected to the very high amount of compressive stresses I'm taking, and most of the deformation processes, if you see here, say if you take the rolling process, if you take the forging, okay, so extrusion, so all these things we are applying the huge amount of compressive stresses, and because of that, material will flow like a liquid. The stress at which the material will flow like a liquid. Okay, so this is the instantaneous stress which is induced in the material, which will cause the material to flow like a liquid, and that is the name of that stress, is the flow stress. Okay, and yes, that stress is actually considered as an averaged property for that particular, whatever the strain which is induced in the material. And that is why whatever the work done we have calculated as k epsilon f to the power n plus 1 divided by n plus 1, that should be equal to the work done which is calculated on the average basis, right? So these are same only. Okay, you will get the idea. When your flow stresses we require, this stress is very very important. When you talk about this flow stress, dear students, so this load, this stress is very very important when we take the calculations of load. Okay, any bulk deformation process, you take any bulk deformation, you take the rolling, you take the wire drawing, you take the extrusion, you take forging. So whenever they will give you in the example, okay, flow stress, okay, so this is the stress, or sometimes they will simply give the yield strength of the material. Okay, so in that case actually what is like they are trying to say, so the material is having, the material will having the deformation at the yield point itself. So that is how the you can assume that the yielding point of that particular material, you can take it as a flow stress of the material. Or if not, if the material is strain hardening, material is going to harden during the deformation, it will going to show you the strain hardening effect. So definitely we can calculate the strain flow stress for particular the strain hardening materials. So if they definitely they will give you in the question, if the material is strain hardening or strain hardened, okay, the material जो भी दिया है आपको, ये स्ट्रेन हार्डन अगर हो सकता है, तो डेफिनेटली दे विल प्रोवाइड यू सम वैल्यूज ऑफ द के, दैट इज स्ट्रेंथ कोएफिशिएंट, और they will provide the value of this strain hardening exponent, or simply they will provide you the equation, say sigma t is equal to k into epsilon to the power. So based on this equation you can now go and calculate the flow stress of the material, and that flow stress of the material you can utilize in the particular calculation. So it may be load calculation, force calculation, or the power calculation. You need to take this flow stress. Okay, you just calculate first and then you use in the formula, right? I will take the example based on this flow stresses. Okay, generally they simply say the flow stress of the material, definitely in out of 100 question, in 95 question in the forming processes, they will directly give you the value of the flow stress. Okay, that stress which is actually responsible to cause the deformation in the material in the strain hardening region. Okay, and that stress we want to calculate the load. I hope it is clear, Vikas. I hope it is clear. We will take the examples on that. Okay, So whenever there is flow stress, directly you can take replace the sigma y by the sigma flow. Okay, directly given. If the some things they have given in the question which are very useful to calculate the sigma f, definitely it is a signal from them that you need to calculate the sigma f first and then use that sigma f in the particular formula. Fine. And one more thing, when you talk about this equation sigma t is equal to k epsilon to the power n, so you need to again identify or need to keep it in mind this stability in tension. No doubt we can able to derive its stability in tension. What it says that at the ultimate point, at the breaking point, or at the maximum loading condition here, the strain hardening exponent is equal to true strain. Don't forget, this is also very important relationship. We need to use this. You just need to understand the wording of the question. If you understood, again you will the word become very easy, because at that, see, at this point particular, at the ultimate strength of the material, say this point, okay, or this point, see, this is the point in the stress strain curve having the maximum stress, okay, which is a sigma ultimate, and this is the point in the stress strain curve having the maximum load. So here p is maximum. Okay, so definitely dp will be 0 at this particular point. Change in load is 0, and from here the necking is going to start, and finally there will be the failure. So please remember, at this particular point, dear students, so whatever the strain hardening exponent n and strain at this point, these are equal, these are same. N is equal to epsilon. So whenever in the question the wordings are like this, so at the ultimate strength of the material, at the maximum loading condition, at the ultimate point, or at the necking condition, at the failure, so such a wordings are there. Definitely you have to assume that n is equal to epsilon, n is equal to epsilon. Okay, KK, very good afternoon. Yes, come on dear student, join the session. I'm good. Okay, fine. So please remember, so such a wording is there. We are going to use the relation, that is strain hardening exponent and the epsilon. Those are same things. Okay. So see, these are the very important things we have to understood in the fundamentals of metal forming. Now the come to the stress and strain relation. See, sigma n is the nominal or normal stress. You know very well, normal stress, and sigma t is the true stress or instantaneous stress. You know that. Say epsilon or E is what? The nominal or normal strain. And say if I take the epsilon as the true strain, you know the relationship between these. Okay, that is, you if you know the sigma t, which is the sigma true, which is equal to sigma nominal into bracket 1 plus E. This is one very important formula. Then if you have the strains, the true strain is equal to ln of 1 plus E. This is also very important relationship. And dear students, what is epsilon? We can calculate true strain is equal to ln of A original divided by A final, that is original cross section area divided by final cross section area, which is equal to ln of final length divided by original length. See, simply from the volume constancy we can write A naught L naught, sorry, A naught L naught is equal to A final L final. So A naught L naught is equal to L final divided by L naught. So based on that, we can directly write epsilon is equal to ln of A original by A final, or ln of L final divided by L original. Okay, I'm good, Taggy. Yesterday, that is the reason why I take the rest. So that is the reason why I could not able to take the yesterday session. The throat was so much paining. Right, right. Now see, when you get these things clear, that is the relationship between the nominal and true, okay, normal or true stress and strain. definitely we need to understand the strain rates. Okay, if I write here the epsilon or E dot, which is nothing but the normal strain rate, that is the strain per unit of time, which is nothing but dE by dt, which is equal to d dt of what is E? E is what? E is what actually? Change in length divided by original length. Okay, so if I write here, or here if I take change in length, L final minus L original divided by original length. Okay, so nothing but see this change in length, nothing but some length is there. Okay, change in length is what? Ultimately length is there. So if I write here dl by dt is what actually? Okay, and this is 1 upon L naught is there. So it will be what? See, change in length divided by change in time. dl by dt is what? Nothing but the velocity. So see here, velocity divided by original length. So this is nothing but v is the velocity of deformation. Velocity of deformation divided by original length. Original length of the specimen or workpiece. Original length of specimen, dear students, this is nothing but your strain rate, nominal strain rate. Okay, so which is equal to nominal strain rate is equal to velocity of deformation divided by original length. And when I talk about the true strain rate, epsilon dot is equal to d dt of what? Epsilon, that is the true strain per unit of time, which is equal to d dt of what is true strain? Ln of L final divided by L original. You know this. So definitely if I rearrange this equation, I will get say 1 upon L final into again say dl by dt, which is nothing but velocity of deformation. Velocity of deformation divided by final velocity or instantaneous velocity. Final or instantaneous velocity. Instantaneous length if I take. So this will be the true strain rate. True strain rate is equal to velocity of deformation divided by final length. Please understand the relation. Please understand the relationship. Very, very important. Very, very important. Okay. So these are all the very fundamental things about the metal forming. You need to understand this. You need to understand this. Once you understand this, definitely the same things whenever, as and when required in the calculations in the bulk deformation processes, you should use that. You should use that. Right? I hope it is clear. I hope it is clear. Shall we go for now solving the questions? Shall we go, please? Tell me how many people are there? Yes, thoda like karo bhai. Thoda thumb dikha do so that I can understand you are there. We will go for solving the questions. We try to go on the fundamentals questions. Yes, nominal and engineering same. Nominal, normal, engineering are same. Okay, true or instantaneous? True or instantaneous? Bus. So there are so many people who are watching. Okay, take this question. Take this question. Determine the work done if the bar of 20 mm diameter and 60 mm in length is elongated by 12 mm. The yield strength of the specimen after elongation if the material work hardens according to the law sigma is equal to 250 into epsilon to the power 0.3. Neglect the elastic deformation. Yes. So what is given? Sigma is equal to, yes Vikram, 250 into epsilon to the power 0.3. Okay. So here tell me what is the initial length? Original length 60 millimeter is there and elongated by. So elongation in the specimen will be how much? 12. So they say here is 6 and here is 6. So definitely, so L final will be 60 plus 12. That will be how much? 72 mm. 72 mm. That will be the L final, isn't it? I hope it is clear. Now, diameter, original diameter is how much? So original diameter is D original is 20 mm. D original is 20 mm. But for us, length is enough. If you have final length and original length, so you can definitely calculate the true strain. How to calculate true strain? True strain is equal to epsilon is equal to ln of what is there? L final divided by L original. We can very nicely calculate. Tell me what value and be there with the calculators. Be there with the calculators. I want respond from you guys in the chat box. Ln of final length will be 72. Okay. Divided by original length 60. Tell me what is the strain, true strain induced in the specimen. Calculate and tell me the true strain induced in the material. And what is the relation? If sigma is equal to 250 into, इधर लिखता हूं मैं, sigma is equal to 250 into epsilon to the power 0.3. So n is how much here? See here, n is how much here? N is 0.3 and true strain is how much you are getting here? 0.1823. 0.1823. Akhilesh Khadse, 0.1823. Yes, so this is the true strain you are getting here, right? Now tell me what is the this they are what they are saying. They are saying either the true stress or the yield strength of the specimen after elongation is given by this formula. If the see if the material is work hardened, so whenever material is work hardened, this is obeying this particular law, Floker equation, Holomon-Ludwig equation, or the power law. You can write like this. You know that. Now you tell me what is the true stress or the true yield strength of the material. That is 250 into epsilon. Epsilon is how much? 0.1823 to the power n 0.23. Tell me the value of sigma. How much sigma you are getting here? Yes, 150. Sigma y you are getting as 150 here because they are saying it is the yield strength. Very good, very good. 150 Newton per mm square. Now tell me how to calculate the work done. You know the how to calculate work done. They are asking. They are asking you to calculate work done. Simply work done means what? You should calculate in terms of Newton meter. That is in terms of joule only. They are not saying calculate in terms of Newton per sorry, say megajoule per meter cube or work done per unit volume. They are not saying like that. Simply we have to calculate the work done. That is in joules or in terms of Newton meter. Tell me how much it is. So work done, you know how to calculate. Work done is equal to what is formula? K into epsilon to the power n plus 1, epsilon f to the power n plus 1 divided by n plus 1. So tell me what is the strain there, what is the strength coefficient, K value is how much? K value is how much? Is this 200 or 250? 250 is the strength coefficient given. Epsilon f is how much? That is a strain in the material 0.1823. 0.1823 to the power n is how much? N is 0.3 plus 1 or 0.3 plus 1 divided by 0.3 plus 1. So tell me how much it is. Tell me how much it is. 250 into 0.1823 to the power 1.3 divided by 1.3. See dear students, today and tomorrow complete metal forming. We are trying to solve each and every type of question. Yes, Ananya, which kind of formula you are writing there? Height into force. Yes, how much work done? So this work done, dear student, this work done you are definitely getting in terms of what? work done per unit of volume. Work done per unit of volume. Yes, 21.03 something. Yes, 21.03. It is megajoules per meter cube. Per meter cube. Okay, please remember this is megajoules per meter cube. So definitely you want the work done only in Newton meter. So tell me in Newton meter how much it is. So work done. So work done in Newton meter. Suppose I gave you the option in terms of Newton meter. So tell me. So this work done 21.03. This is megajoule per meter cube into volume of the workpiece. What is volume? You take initial volume, final volume, or instantaneous volume in between. So metal forming, there is no any change in the volume. Volume is to be get constant. Volume constancy principle is valid. So tell me what was the initial diameter? Pi by 4. Initial diameter 20 mm. So 0.020 square into length. Initial length was how much? Initial length of the part कितनी थी भाई 60 mm. So into 0.060 h, that is the height. So pi by 4 diameter square into height. Tell me now. So this will be in meter cube. This will be in meter cube. Tell me the answer in Newton meter or the answer in joules. Tell me now. 21.03 into solve this all this volume and tell me how much you are getting? How much you are getting? So how much Newton meter? How much Newton meter? Jay, Vikas, very good Indra Kumar, very good Vikrant. It is in megajoule per meter cube, dear. So unless you multiply with the volume, unless you multiply with the volume of the product, it could not become in terms of the joule. Please remember this. I already told you. So whatever this formula is, formula based on the area under the stress strain curve, the area under the stress strain curve, and we converted into modulus of that, say energy absorbed up to the failure point, which is nothing but the toughness. So we need to multiply by the volume of the material, okay, the specimen. Then you can get the answer in Newton meter. Yes, 398, 396 point actually, 396.57, 396, 396.57. This is the answer, 396.57. Yes, everybody got this answer. Everybody, please understand. So this is the work done actually in terms of joule or Newton meter. This is the final answer. So this is also answer. This is also answer, but this answer is what? Megajoule per meter cube. That is why I told you the units and how to convert that units. I told you already. See here, I clear all these things. See this slide. I covered all the things. Conversion of unit. I already told you. Okay. Yes, or 3.96 kilojoule, 0.396 kilojoule, 396 joule or Newton meter. That is the correct answer. I hope it is clear. I hope it is clear, dear students. See, these are the very important things. If you understand these things, no one can stop you, okay, from taking this out of mark from the metal form. I hope it is clear. I hope it is clear. Shall I go for the next question? 396.57 joule. और 397 बोलो तो भी चलेगा, कोई इशू नहीं, कोई दिक्कत वाली बात नहीं. अरे भाई बोलो तो सही. अरे आया कि नहीं? किधर मत जाना भाई. कंप्लीट कर देंगे 2 दिन में. Shall I go for the next? जरा सब लोग मिलके बोलो भाई, सब लोग मिलके बोलो. यस सर, कुछ तो दिखाओ, थम दिखाओ, दिल दिखाओ, कुछ भी दिखाओ सर. थोड़ा माहौल क्रिएट करो भाई, माहौल क्रिएट करो अपना. Take the next question. Yes, so see, now tell me. I am not going to solve. I am not going to solve. You are going to solve this question. You are going to solve this question. अरे विकास, डोंट वरी डियर, पीडीएफ तुरंत मिल जाएगी। देखो वहां पे आपको लिंक भेजा गया है टेलीग्राम चैनल का, देयर विल बी द ऑल मटेरियल अवेलेबल फॉर एवरी दिस यूट्यूब सेशन, you will get the material there, don't worry about that. Take the question, I want the answer from you guys. See, they particularly describe there the unit, the ideal plastic work of deformation per unit volume. So it will be in megajoule per meter cube. Megajoule per meter cube. Tell me the answer. Answer चाहिए मुझे. Yes, next question लिया तो विक्रांत, solve this. A flow curve of the annealed material is expressed as this sigma is equal to 200 into epsilon to the power 1/4. Okay. ट्रू स्ट्रेन कितना दिया है? ट्रू स्ट्रेन एप्सिलॉन इज गिवन 0.3. वेरी नाइस. देन टेल मी द आइडियल वर्क. जल्दी निकालो, जल्दी निकालो. सो सिग्मा इज इक्वल टू 200 into what? The true strain is 0.3 to the power 0.25. Yes. Tell me the sigma value or sigma t value. How much it is? How much it is? So 0.3 to the power 0.25 into 200. It is 148. 148 how much? 148 Newton per mm square. Isn't it? Yes. Yes, Indra Kumar Davle. Very nice, Davle. Very good, very good. So what is the work done? You know very well. Work done per unit volume. Work done per unit volume. What is that? K epsilon f to the power n plus 1 divided by n plus 1. So K is how much? K 200 into epsilon f. It is 0.3 to the power 0.25 divided by 1.25. Tell me how much it is. How much it is? Excellent, dear students. Excellent. How much it is? 35.52. 35.52. This is the work done per unit volume. And you know what is the unit? Megajoule per meter cube. You know that. 35.523. It is megajoule per meter cube. Please, dear students, come on, solve it. Do it by your own. Take that confidence. Boost your confidence. Yes, this is the work done. How much? 35.523 megajoule per meter cube. Excellent, dear student. Excellent. Very good. This is the answer. So, see, megajoule per meter cube. Yes, 35.5. This is the answer. I hope it is clear. I hope it is clear. I hope it is clear. So shall I go for the next question? Shall I go for the next question? I will go to the next question. Take this question. Take this question. Very nice question, dear students. Very nice question. A cylindrical test specimen of the diameter 10 mm and the gauge length 50 mm is extended to 65 mm. Full stop is must. Full stop is must. Yes. Determine the true strain. Okay. We will determine, neglect the elastic deformation. Okay. That is we are neglecting. I already told you this is very, very small. That is why we are neglecting. Okay. If the ultimate strength occurs at 25,000 Newton and the extension of 70 mm. Okay. Determine the strain hardening exponent N and ultimate strength of the material. Very nice question. Very nice question. Try it. Try it. Try it, dear students. So I hope the question is now in front of you. Now the question is in front of you, dear. So I will write here some input data. What is original length they have given? 50 mm. And original diameter is how much? 10 mm. Okay, no issue. I will take it. And now this specimen is extended to what final length? Extended to the final length how much? 65 mm. Okay, 65 mm. Now from this data you can one thing you can do very nicely and very fastly. क्या निकालोगे जल्दी से? ट्रू स्ट्रेन निकाल दो भाई. ट्रू स्ट्रेन निकालो. क्या आएगा? ln of final length by original length. Final length upon original length. You know it better. अरे भैया बाबा बताओ तो सही, ये कितना आया? ln of 65 भाग्या 50. बताओ 65 को मैंने 50 से डिवाइड किया और उसका नेचुरल लॉग लिया तो कितना आएगा? ओए अखिलेश खड़से, अखिलेश कुमार, it is 0.26. very nice. 0.2623. very nice Vikrant Lakshman, very good. So this is our true strain. Okay, this is our true strain. Now dear students, they are saying that okay, this is okay, initial condition. Now they are also saying that it is extended to what? See, if the ultimate strength will occur at the load is how much? Force is given 25 kilonewton. Okay, and at extension of final extension, again at the extension of 70 mm. Okay, no issue. We will calculate the Nikita Joshi. What you want to say? Nikita Joshi, what you want to say? I hope this is for you only. So please dear students, don't show me such a kind of activity. Okay. So we are striving for your goodness. Okay. We our entire team from the Gradeup. Okay. Don't show such a kind of thing. Tell me. Okay. Now at the extension of how much? At the extension of 70 mm. Okay, at the extension of 70 mm, tell me true strain will be how much? Now they are saying that the extension of 70 mm from 50 mm. Tell me how much it is ln of 70 divided by 50. L final divided by L original. Original लेंथ कितने अपनी 50 है, फाइनल लेंथ अभी कितनी है 70 mm. So यहाँ पे अपना कितना आया? True strain it is 0.3364. It is 0.3364. Isn't it? Very good, very good. Yes. चलो भाई बताओ कितना है आप? सो स्ट्रेन विल आपको, सो ये स्ट्रेन क्या होता है भाई? स्ट्रेन इज नथिंग बट आई टोल्ड यू ट्रू स्ट्रेन इज इक्वल टू ln ऑफ a original by a final, or it is nothing but ln of L final divided by L original. So can we calculate now the area of cross section at the maximum load. Can we calculate the area of cross section at maximum load? निकाल सकते हैं इतना? Yes, tell me. So can I write here this epsilon now how much? And n is how much here? At the maximum loading, n at the maximum loading or at the ultimate strength. Okay, it is equal to epsilon. So tell me epsilon is equal to how much? So n is equal to epsilon is equal to 0.3364. Okay, because at the ultimate they have said that the load is how much? Now they have used 25,000 Newton and the extension length goes up to the 70 mm. So can we calculate the area corresponding to that? So e to the power, if I definitely write here, strain is how much? 0.3364, which is equal to ln of A original divided by A final. A final we need to calculate, and tell me what is A original. Ln of A original what? Pi by 4. Pi by 4 diameter is how much? 10 mm. 10 mm. Pi by 4 d square divided by A final, which is equal to 0.3364. Tell me the value of A final. Tell me the value of A final. Yes, tell me. Check it out, this question. Say they want at the ultimate point. See, ultimate strength occurs. They are saying ultimate strength occurs at 25,000 Newton. Means the strength definitely at 25,000 load is at ultimate point, and at ultimate what is the extension? 70 mm. So definitely at that particular point, at the ultimate, that strain is equal to what? The true strain is equal to strain hardening exponent. Strain hardening exponent, isn't it? Tell me one thing, why this message is held for review? So frequently it is coming like that. So anyone have some issues for this session? So I'm not actually getting why this message is frequently coming. Anyone have some issues? So don't attend this simply. See, many times I don't know why. Yes, now tell me final values. Tell me jaldi se. Yes, tell me. So final area will be how much? Now why some people are try to spoil the party? I don't understand. Some people try to spoil the party. This is not good actually. Tell me what is final area. So dear, if you calculate final area will be how much? 56.104 mm square. And then finally we can calculate, they are asking to calculate the ultimate strength. Ultimate strength. So ultimate strength will be how much now? Ultimate load is how much? Sigma ultimate. It will be the force at that point, ultimate point, divided by the area at ultimate or area at final. So tell me force is how much? 25,000 divided by AF 56.104. So tell me what is the ultimate strength? Tell me the ultimate strength very fast. Yes. Chat box should be move on. Chat box should be moving. Anubhav very good. Vikas very good. Jay Kumar, Lakshman, Tyagi Sahib. Then tell me ultimate strength. Sigma ultimate will be how much? That they are asking. 445.60 megapascal. Yes, that is the answer. Yes, 456, 445, 445.6. Excellent, excellent, excellent. See what they are asking. Determine the strain hardening exponent that we already determined. Okay, strain hardening exponent already determined. N is equal to epsilon. We know from this regards we calculated the N value, and ultimate strength we calculated as sigma is equal to force upon area. So force at the ultimate 25,000 Newton, and ultimate area we have calculated like this 51 or 56.104. Yes, yes, absolutely correct. 445, 445. Good, 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 good. Take this next question. Take this next question. Yes, tell me the value. The metal body is in the plastic state. The metal body is in the plastic state under the action of the following stress state. T is given as 120, 60, 40, 60. Yeah, these are the stress state given. What they are saying, determine the yield strength of the material in the tensile and shear according to the von Mises yield condition. Von Mises yield condition. The stresses are given in the megapascal. Okay. So you know that. So you know that, dear students, uh, the strain, this stress strain theories. Okay, the stress cast maximum shear stress theory. You know, then you know the von Mises distortion energy theory, dear students. You know. Okay, based on that, this question is there, right? I hope you know all this. That is, say the shear yield strength coefficient or shear yield strength K is equal to tau max is equal to what? You know that, say sigma 1 minus sigma 3 by 2. Okay, that will comes to K is equal to say 0.5 times of sigma yt, and this is from the Tresca's criteria. Okay, and K is equal to 0.577 times sigma y of yt, which is from the von Mises criteria, isn't it? You know this very well, isn't it? So how to solve this? So this is the how, this is sigma 1 1, this is sigma 2 2, this is sigma 3 3, this is sigma 2 1, sigma 2, sigma 1 2, sigma 1 3, this is sigma 2 1, this is sigma 2 3, this is sigma 3 1, sigma 3 2, and sigma 3 3, isn't it? So all the diagonal stresses that we are having, dear students, isn't it, which are sigma 1 1. See, so these are the stresses. If we have the principal stresses in terms of principal stresses, how we are right? Sigma 1 and sigma 2, sigma 3 are the principal stresses, such as that sigma 1 is greater than equal to sigma 2 is greater than equal to sigma 3, right? So from that we know how to get the relationship for the Tresca's criteria and the von Mises distortion criteria. Okay, that is, say sigma 1 minus sigma 3 by 2, which is the tau max. And what is the strain energy per unit volume? Epsilon is equal to 1 upon 6g into bracket sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, which is equal to say some constant C, okay, isn't it? Or which is equal to say some A, right? So we will get here 6GA, which is equal to get 6GA, which is again get some constant C. So constant C we can say is equal to sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. In terms of principal stresses I am writing. And you know that, dear students, to understand the property of the material, we are always considering the uniaxial tension. Okay, so sigma 1 is equal to sigma yt, sigma 2 is equal to sigma 3 is equal to 0 in uniaxial tension. Therefore, in this equation, in the equation A, suppose I can write now sigma 1 is equal to sigma yt, say sigma yt minus 0, okay, square plus sigma 2 minus sigma 3 0 square plus sigma 3 minus sigma 1, this is sigma yt square is equal to C. So this will be 2 sigma yt square is equal to C. Okay, so this is equation number say 1. And dear students, again from the pure say, if you say the pure torsion, okay, when you consider the pure torsion again, where sigma 1 is equal to K, whereas sigma 3 is equal to minus K, and sigma 2 in between sigma 2 is equal to 0, we will get the more circle like this, isn't it? That is, this is K and this is minus K. This is sigma 1 is equal to K, this is sigma 2 is equal to, or sigma 3 is equal to minus K. This is tau, isn't it? So from this condition, if I take sigma 1 as a K and sigma 3 as a minus K, okay, so again I will get this C is equal to, that is K, okay, sigma 1 minus sigma 2 0 plus square plus sigma 2 0 minus sigma 3 minus K whole square plus sigma 3 which is minus K whole square, which is equal to C, which is equal to 6K square is equal to C. Say this is equation number 2. And we equate this equation number 1 and 2. If we equate this equation number 1 and 2, that is what? This is 2 sigma yt square is equal to 6K square, isn't it? So we will get this sigma yt square is equal to 3K square, or K is equal to what? 1 upon root 3 times this sigma yt, which is nothing but what? K is equal to 0.577 times sigma yt. One Mises condition, isn't it? I hope it is clear. Now, dear students, in terms of the stresses, if you want to write the same 6K square equation, same this equation if I want to write, so it will be 6K square is equal to, into bracket, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, okay, plus 6 times sigma 1 square plus sigma 3 square plus sigma 1 square. Put the values, tell me how much sigma 1. Sigma 1 means how much? Sigma 1 in the question, in the matrix is given, state of stress is given. Check it out. See, these are sigma 120, sigma 2 minus 100, sigma 3 80, sigma 2 is 60, sigma 3 is 40, sigma 1 is 60, sigma 3 is 30. Like that, simple, very simple thing. Tell me the values now. And just put here, sigma 1 is how much? Sigma 1 it is 120 minus sigma 2 minus 100 whole square plus sigma 2 minus 100 minus the sigma 3 80 whole square plus sigma 3 it is 180 minus sigma 1 it is 120 whole square plus 6 times say sigma 2 is 60 square plus sigma 3 30 square and plus sigma 1 it is 40 square. Tell me the values and final value. K 6K K square is equal to how much? And finally tell me what is K. Okay, once you get the K, you know the relationship by the von Mises distortion theory. They are saying, yes, according to the von Mises yield condition, we can get the yield strength of the material sigma yt How much K value? Tell me very fast. How much K value? How much K value? Tell me. Now K is how much? Please come on, dear students. Make the calculations. Make the calculations. Yes, dear students, tell me. Jai, KK Tyagi, Vikrant. Yes, 140, 140.83. 140.83. Yes, 140.83. 140.83. That is correct. This is the yield shear strength. Yield shear strength. Now you know that K is equal to what? 0.577 times sigma yt, isn't it? Or sigma yt is how much? So sigma yt we know, we want actually. So 140.83 divided by 0.577. How much sigma yt? What is the answer? What is the answer? Yes, dear students, tell me the answer very fast. So how much this yield strength? Is it 243? 243.92 Newton per mm square. Yes, that is correct. Yes, yes, correct. 243.92, 243.92. Yes, come on, dear students. 244. Yes, 244 because correct. Abhinandan Kumar, very good, very good, very good, dear students. Yes, very good. Take the next question. Take the next question. Solve this question very fast. Very fast. Solve this question. Yes, tell me the value. Answer, tell me. So here, see, very easy question. If the true stress strain curve of a ductile material represented by sigma is equal to this 1100 epsilon to the power 0.2. Okay, the ultimate tensile strength. Okay, ultimate tensile strength, or simply our engineering strength. Okay, so of course this is the strength you are getting. Sigma T is equal to this K, that is 1100 into epsilon. Epsilon is how much? At the ultimate point, dear student, you know that N is equal to epsilon. N is equal to epsilon, isn't it? At the ultimate, you know that N is equal to epsilon. So 0.2 to the power 0.2, it is how much? It is how much? 1100. 0.2 to the power 0.2 into 1100. So you are getting at 797 megapascal. So this is the sigma T true, dear student, true stress. But our engineering is what? Sigma N, isn't it? This is our engineering ultimate strength. Engineering ultimate strength. Okay, engineering ultimate strength. So sigma N is equal to what? Sigma T into bracket 1 plus E. Okay. And you know that epsilon is equal to what? Ln of 1 plus E. 1 plus E. Isn't it? Ln of 1 plus E. So tell me how much E here? Or ln of 1 plus E. Epsilon is how much? 0.2. 0.2 is equal to ln of 1 plus e. So I can write e to the power 0.2 is equal to 1 plus e. So this is the e for exponential and this is e for strain. Don't confuse it. So you know that sigma n is equal to sigma t into bracket 1 plus e. So sigma t is how much now we have calculated? 797. 797 into bracket 1 plus e is how much? 1 plus e already there. 797 into 1 plus e is what? E to the power 0.2. So this is our nominal ultimate strength. How much it is? So shift e to the power 0.2 into 797. It is 973. Yes, it was here. It was here. Actually, this is written as 973. Okay. Yes, how much it is? 973. 973. So many of the you people, why it is 797? This is the true stress. This is the true stress. Okay. We want the value of ultimate strain. There they see in bracket they have mentioned. They have mentioned engineering. They want engineering. They don't want true. They want normal or nominal stress. Okay, they want nominal ultimate strain, which is sigma n, which is sigma n. Yes, excellent, excellent, Abhinandan. Abhinandan, very good. Jai Kumar, it is not 797. It is not 797. I hope understood. See, confusion. वो आपको घुमाएगा और घूमेंगे ऐसा नहीं होना चाहिए, राइट? So it should be 973. 973. I hope it is clear. I hope it is clear. 973 is correct answer. 973 megapascal. Because they are saying not the, if here the word is true, they definitely calculated is the final answer. But they are saying it is engineering. It is engineering. So engineering is nothing but sigma n. Sigma n, you know the relation. I told you this relation. Sigma n is equal to what? Sigma t into 1 plus e. 1 plus e we can get from here. Isn't it? 973. Excellent. Very good. Come on, dear student. Join this session. Very helpful to you. I hope it is clear. भाई लोग कुछ मजा आ रहा है कि नहीं? क्वेश्चन सॉल्व हो रहे कि नहीं? अरे भाई क्वेश्चन सॉल्व हो रहे कि नहीं? ऐसा लग रहा है कि नहीं भाई? हाँ चल रहा है, ठीक चल रहा है. Is that clear? Excellent. Very good. Very good. Come on, take the next question. I hope this question was very important so that don't do any hurry. Okay. Understand the question. You know everything now. You know each and everything. Just don't do any confusing work. Understand the question and just go on solving. Take this question. Tell me the answer. Tell me the answer. Now once again, true stress, true strain, behavior of the metal is given as. Vikas, which formula? Sigma T? Yes. Sigma T 797 we have taken, no? Sigma T, yes. Sigma T, this is 797. This is the true. And this is the nominal or engineering. That is the ultimate strength. Engineering ultimate strength. Okay. Yes, here it is given sigma is equal to 1750 into epsilon to the power 37. So the true stress at the necking, you know that, at the necking. So at the necking, that is n is equal to epsilon. So n is what? 0.37, which is nothing but the epsilon. So calculate sigma true. They are asking the true stress. Sigma t is equal to 1750 into say 0.37 to the power 0.37. Yes, now here no any confusion. If here I say I want the nominal instead of 2, if I say the nominal, then again calculate 1 plus e. Right? Yes, absolutely correct. Vikrant, very good. So 12 megapascal. 12 megapascal. Sigma it is how much? 12 11 मेगा पास्कल. Very good, very good, very good, dear students. Come on. Excellent, excellent work by you guys. Next question. See, the ultimate tensile strength of the material is ultimate tensile strength, which is nothing but sigma n. It is given as 400 megapascal, isn't it? Good. And the elongation up to maximum load, elongation is there in whenever elongation is percentage with the original, change in length by original length with the original, definitely there is a nominal strain. Strain is given as 0.35, isn't it? Yes, very good, very good. The material obeys the power law, that is the strain handling law. Then the true stress true strain relationship in the plastic deformation range, how much? Okay, so now we need to find out this flow curve equation, which is nothing but sigma t is equal to k into epsilon to the power n. So very nicely we can calculate sigma t is equal to sigma n into bracket 1 plus e, isn't it? So sigma n is how much? It is given 400 into bracket 1 plus e is how much? 0.35. So tell me 400 into 1.35 is how much? 400 into 1.35, it is 540. So you got here the true stress as 540 megapascal. Okay, now the equation says sigma t is equal to what? K into epsilon. Say what they are saying, if the material obeys the power law of handling, then the true stress true strain in the plastic deformation zone. So of course, dear students, here the ultimate tensile strength of the material and the elongation up to the maximum loading. See, this word is very important. I told you, you need to understand the meaning of the wording in the numerical. Okay, so of course here they are interested in what? The maximum loading condition. Definitely our the stability in torsion, stability in tension is valid here. Okay, at the maximum loading, at the necking condition, all these words are directly indicating you this theory or stability in tension. You take n is equal to epsilon. So I will highlight this word here, this word. Okay, now go on solving the question. Now you got here, see, now you want here k value. K value definitely 540 is not there. It is sigma t value is 540. So definitely k into epsilon is what? N is now equal to epsilon. So n is how much here? So n is definitely epsilon. So epsilon is how much? You need to calculate the epsilon. How to calculate epsilon? So epsilon is equal to what? Ln of E is no. E is known to you, ln of 1 plus E. So epsilon is what? Ln of 1 plus E is how much? 0.35. So tell me what is ln of 1.35? This is our true strain. So it will be 0.3. So you are getting here 0.3. Now here if I apply sigma t is equal to k into epsilon to the power n. See epsilon sigma t is how much? 540. 540 is equal to k is unknown. K is unknown into true strain is how much? 0.3. 0.3 to the power n is how much? So you know that for the maximum loading condition n is equal to epsilon. Okay, so 0.3 to the power 0.3. Tell me 0.3 to the power 0.3 and 540 divided by answer. You will get the K value strength coefficient at 774.9, which is equal to 775 megapascal. Isn't it? Now very nicely you can write the flow curve equation. What you have got? Now the flow curve equation or power law we can write as sigma t is equal to k is how much? 775 into epsilon to the power n kitna tha re? At maximum loading condition 0.3. So this is your final flow curve equation. Tell me the value, tell me the answer. Option 775 into epsilon to the power 0.3. 775 to the epsilon power 0.3. B Bombay is the answer. B Bombay is the answer. Vikrant, not C is the answer. C is not the answer, dear. B Bombay is the answer. B Bombay is the correct answer. I hope this is clear, dear students. Please understand. whenever in the question, please understand. So wording I will write it here. कौन सा wording? At the breaking point, at the breaking. This is one statement. At the maximum loading, at the maximum loading. Okay. Then at the failure, or at the necking, So such a kind of wording is there. Definitely they are indicating you take n is equal to epsilon theory of stability. Theory of uh, stability in tension. Okay, instability in tension actually value, because see after that particular why it is unstable, so after the sigma ultimate it is start necking. Okay, so necking is there. Instability in tension, this is instability in tension, please understand. I hope it is clear. Take the next question. Take the next question from the Nadai's equation, please. From the Nadai equation. Tell me, I already given you the formulas for the true strain rate and the nominal strain rate. So how they are related? Tell me the answer very fast. According to the Nadai, whatever the equations that we have, velocity of deformation, okay, divided by the original length, which is the nominal strain rate, and the velocity of deformation divided by final or instantaneous length, which is nothing but the true strain rate. Now tell me what is the answer for this. So this actually experiment done by the Nadai, and this equation for the strains rates equation for the strain rates given by this Nadai experiment, that the cross slide is moving. Okay, so that will give the velocity of deformation, and whatever the heights we are having, either the original height or original length or the final length, from that we will get this expression. Sidhu, very nice. Sidhu, tell me how it is getting solved. Come on, tell me how we are going to solve this. Come on, you know that the E dot is equal to what? The velocity of deformation divided by original length. And you know that epsilon dot as what? Velocity of deformation or divided by final length. Okay, so can we write velocity as E dot into L naught? Yes, I will write velocity as E dot into L naught divided by L final. So it will be E dot divided by L final. If I take this L naught to the denominator of denominator and just I do some mathematical thing, I will subtract one and add one. Tell me to the denominator what will happen. E dot divided by L final minus L original divided by L original plus 1. So epsilon dot is equal to what I can get? E dot divided by what is this? Change in length by original length. It is nothing but the nominal strain. E plus 1. Tell me the answer. This is the answer. So which option is correct? Which option is correct, dear students? Please participate. So whether B Bombay is correct, B Bombay is correct, B Bombay is correct. Excellent. B Bombay is correct. Very nice, Lakshman. Very nice. Yes, dear students, very nice, very nice. Please respond me, dear students, in the chat box. Chat box should be moving. Move on the chat box. Take this question and tell me the answer. A specimen is compressed from the original height 50 mm with the crosshead of the press moving. It's not morning, it's moving. It's moving at 0.12 meter per second as per Nadai mathematical conditions. If the bar current height is 30 mm, the true strain rate. See, for true stress, there is a relation with the true stress. There is a relation between true stress and K. Okay, that is stress, normal stress. This engineering stress or normal stress sigma n is equal to this true stress sigma t into bracket 1 plus K. Sigma t, that is the by the Flocker equation, which is equal to strength coefficient K into epsilon to the power n. So this is the true stress and this is the nominal stress. But how the true stress and nominal stress are relating with each other like this. Sigma n is equal to sigma t into bracket 1 plus. Okay, Sidhu. What is that, Vikrant? Yes, tell me the answer for this. Yes, I that you know that what they are asking. True strain rate. True strain rate, of course, it is in per unit of second or in second inverse. It will be velocity of deformation divided by the instantaneous or final height. Instantaneous or final height, because this is a true. Okay. So tell me how much it is. Velocity is how much? 0.12 meter per second divided by what is the instantaneous height or current height? It is 30 mm. It is 30 mm. It will be 0.030 meter. So how much it is? How much it is? It is 4. And of course, see, this is why it is minus, because it is a compression. It is a compress, no. So for compression, it is negative. Tension, it is positive. Yes. So 4 second inverse. 4 second inverse. So this is epsilon dot. I hope it is clear. It is why negative? Compression is there. For compression, it is negative. You can have positive for the tension. Okay. Hi Ramisman, how are you? Take the next question. Solve this question. A metal rod of initial length. Initial length was how much? Initial length, L original. The length of the rod at any instant, that is final length. How much it is? L naught into bracket 1 plus t square. Where t is the time in minutes. Okay, the true strain rate. The true strain rate. So what is the true strain? True strain is what? ln of ln of L final divided by L original. ln of L final is how much? L naught into 1 plus t square. L naught into 1 plus t square divided by L naught is the original length. So L naught cancel, ln of 1 plus t square. Okay. This is the true strain. How much it is? ln of 1 plus t square. At t is equal to how much? 1 minute. So 1 plus 1 into 2 into 1. 2 divided by 2. How much it is? 1. Yes, check it out. Very nice. Very easy. Very easy. So this was the gate question, dear students. This was the gate question. So see how we can get the questions in the gate. I hope it is one is clear, one is okay. I hope it is clear. Now, dear students, see. What happened? Yes. So take this question, dear students. Solve this question. Now we have started. See the fundamentals of metal forming is clear. I hope it is clear. Yes, Ramishman. See the strain rate is asked. Yes, that is the correct. We have to differentiate with respect to time. No, that is why Vikrant. Imran Khan. Why we differentiate? Because the true strain rate they have asked. I hope it is clear. See, this is the epsilon. No, we have to d epsilon by dt. D epsilon by dt. So d dt of epsilon is what? D dt of epsilon is what that we have got? Ln of 1 plus t square. So with respect to t, we have to differentiate it. And that is why I differentiated ln of 1 plus t square. And how that is how we got this value of 1. Okay. So see here. So initial length, final length, we got the true strain here. So this was our epsilon. Okay. And now epsilon dot it what? Epsilon dot they ask. Epsilon dot which is equal to d dt of this epsilon. So which is equal to d dt of this. D dt of this epsilon is what? Ln of 1 plus t square. And that is the differentiation 1 upon 1 plus t square into 2t. And then we put the value of t 1. Then we got this value of 1. Sorry, we got the time how much? 1 only, and the answer we got it as 2 divided by 2, which is equal to 1. See in the question, again I have to some marking here that they ask the true strain, not only true strain, it is rate, and it is in minute inverse, of course. I have to emphasize you on this particular statement. This was very, very important. So understand, dear students, please. So so I was just in the flow, I just go on calculating the things like this, but you should understand why I'm going so fast, because I somewhere in the mind this question many times I have it come and gone through my hands. So definitely the intention is same, that is calculation of the true strain rate, but I didn't read actually, truly speaking. Okay, fine. I hope it is clear. I hope it is clear, dear students. So dear students, I hope so. See, the my intention was that why to get this marathon into the 2 sessions, right? So very important session is what? This is the fundamentals of metal form. Okay, the fundamentals. Whatever the things, definitely nowadays we can have. Yes, Abhinand, that is correct. Rate means whenever there is a rate, of course, rate means what? The per unit of time, then it is a rate. Now tell me, from the see many questions you will get at least one question, dear student. At least one question nowadays. If you see any previous year question paper, any previous year question paper, it will be the question on say simply the Holloman-Ludwig equation, simply on the power law. There may be the equation, or there may be the question from the true stress, true strain values, okay, or the relationship between the true and nominal stress strain, okay, or there is a relation between say the von Mises criteria or the Tresca's criteria, okay, or there is a question from the strain rate, okay. So definitely you will have some of the, or at least one question from these fundamentals of metal form. Okay, so I hope uh, based on this based on this thing only, dear students, I approach so many questions which can be asked under this heading, under this roof of fundamentals of metal form. And no doubt the second part is related to the processes. Okay, कौन कौन से processes है अपने पास deformation में? आपके पास rolling. See, if you see the previous year question papers, definitely many times say if out of this, if say the 100% chances, there are more than 70-80% of times the process which is asked is nothing but the rolling process. On the rolling process, definitely you will find at least one question. Okay, and of course there are the other metal forming processes like tube drawing is there, wire drawing is there, then we will be having the extrusion process there, forging is there. Okay, yes, these are the bulk deformation processes there. Yes, Abhinandan, don't worry, dear. See, you can see this rolling question. These are the rolling questions. Okay, based on rolling, then we'll have a wire drawing question. See, not only the ideal case of deformation we have take the questions based on where we have to consider the friction and redundant work. These are such a questions. See, very nice questions we have taken for this marathon. Of course, we are going to solve this. Now, see the fundamentals of the forming. We have covered it, right? Now, the time has to start up with. Now, the time has to start up with the bulk deformation processes, right? And of course, by the tomorrow, we will be covering entire things: rolling, forging, extrusion, wire drawing, tube drawing. So all the processes, of course, we are trying to cover through the numericals. Through the numericals, we have to try to understand some background, some basic formulas about these processes, and we will go ahead. So of course, today at least I have to start the rolling process. The first question you will see here on the rolling. The first question is on the rolling. So I hope you know the all the formulas for rolling. So right now I will just revise you. Yes, tomorrow 2 to 4, dear, please there. Tomorrow again 2 to 4 p.m. we are going to solve all the questions on the bulk deformation process, right? So at least up to this 10-15 minutes we will revise the entire formulas related to the rolling process only, and from say tomorrow 2 p.m. we will start the questions on the rolling, right? So I hope, dear student, the today's session worth or not? Tell me once. So now see, rolling process. I will start the formulas for rolling process. And please let me know which more topics you want for the marathon, so that I can arrange one more marathon. And which topic is very, very important as far as the production engineering? I hope none other than the metal cutting. When we talk about the metal forming, yes, we have to talk about the metal cutting. You tell me when, whether you want the marathon on metal cutting, then definitely I'll be ready. Tell me whether you want metal cutting or some other. I am also planning to have the one marathon on the previous year gate questions from the XC fluid mechanics. XC fluid mechanics. Gate XC fluid mechanics. Gate XC fluid mechanics, only previous year gate questions. So actually for this gate XC previous year gate question papers, there is no such a solution available in the market as far as my knowledge is best. Okay, or whatever the available are not up to the mark. So definitely I was thinking for that session also, so that XC fluid mechanics previous year gate questions. Okay, so this is the original thickness of the strip, this is the final thickness of the strip, and say suppose the width of the strip is this much, and you know that the plane strain condition is valid. Plane strain condition is valid in the rolling operation, dear students. Okay, okay. Definitely metal cutting, definitely will they plan the 2 sessions like the marathon of 5 hours for metal cutting. Okay, this is the roller radius r, so this is the bite angle, say alpha, and this is this is the length of arc of deformation LP. Okay, so now we can very nicely write. So length of arc of deformation LP is nothing but root of r delta h. You know that again, 2r into bracket 1 minus cos of this alpha is the bite angle, which is nothing but what? This is the draft delta h. Okay, then you know that strain is how much? Strain is nothing but ln of h original by h final. This is the true strain you can have in the rolling operation. Now dear student, what is there in the rolling operation? Force calculation, very important. Force calculation, it is nothing but 2 by root 3 into sigma y into bracket b LP into bracket 1 plus mu times LP divided by 4h average. So this is very important force formula, dear students. Okay, so what I will plan at the end of the December, will be covering this one marathon on the metal cutting, and in the beginning of the new year we will be planning the one marathon on, or the practice session on the fluid mechanics. Yes, see, yes, this is the length of arc of contact LP. Okay, length of arc of contact, this is the length of arc of contact, dear students. Okay, you know very well. So just I am writing the formulas, otherwise we can derive it also, no any big deal in that. Simple mathematics or simple geometry is there. Okay, also we can have the analysis, plane strain condition analysis we can do, right? No any big deal, but that is not the time, this is not the correct time for that. Just understood the formulas, note down these formulas, right? Or simply you can write this force is nothing but this sigma y into b into LP, like this also. But see, if you want to go to the nearness to the answer, nearness to the reality, plane strain condition is valid. You know that for plane strain condition, the sigma y dash is equal to what? 2 by root 3 times this sigma y, which is nothing but this sigma y. This is your, whenever material is strain hardened, this sigma y get replaced by sigma flow. We have to calculate the sigma flow first, and then they use the sigma flow into the given formula. Okay, so what I suggest you, dear students, go through this formula. Okay, always keep it in mind, this formula. Otherwise, there are two, three formulas for the force calculation in the rolling operation. 2, 3 formulas. So according to Kalpakjian, also there is some different formula. Kalpakjian, if you are reading the Kalpakjian book, so he says that the force is equal to sigma y into BLP into bracket 1 plus mu LP by 2H average. Simple. This is also the correct formula by the Kalpakjian. This is also the correct formula. But dear students, what I suggest you go with this formula by which where the plane strain condition is considered. This is very important assumption in the rolling operation. Okay, that is there is no any spreading of the sheet along the widthwise direction. Only the deformation we are getting along the lengthwise direction. That is very important assumption. Okay. Why Telegram link is not working, dear? So in the chat box, Telegram link is there. Whatever the PDFs material will be getting there. Join the Telegram channel. You will get notified first. So what Gradeup is planning for you guys, right? So this is the force this is the force, dear students, by the Kalpakjian. I hope you need not to write, need not to remember this formula. You just go through this formula. Okay, this is highlighted yellow formula. Okay, and now once the force is known, dear students, how to calculate power? So power is nothing but this roll separating force into the arm moment, that which is nothing but lambda times LP, where lambda is nothing but the arm factor LP is your length of arc of deformation or length of arc of contact into this 2 pi n divided by 60. So this is the formula for power calculation. Okay, this is the power per roll. Okay, this is the power per roll. When you want the complete or total power in the rolling operation, you multiply this equation by 2. So it will be total power. Right? Okay, and please remember this arm factor lambda, it is generally 0.3 for cold working and it is equal to 0.4 for hot working. And please remember that in the rolling operation, until it is provided or it is given, you should assume that rolling operation is a hot rolling operation. Okay, so these are the very important formulas, dear students, as far as the rolling operation is concerned. One more thing, there is a maximum draft. How to calculate delta H max, which is nothing but the mu square r, which is one more formula. Mu square r is the maximum draft in the rolling operation, right? So please understand. So these are the various formulas. How to calculate the number of passes? You can calculate delta H divided by delta H max per pass. So these are the number of passes here. So all these things definitely we are going to look in tomorrow's session. Of course, from 2 to 4, once again we will be covering the bulk deformation processes like rolling, wire drawing, tube drawing, extrusion, forging. These topic including the sheet metal working, some of the questions from the sheet metal we are going to solve in the tomorrow's session. So be there, join the session, share the session, dear student, like the session. Okay, don't forget to like and share the session. Tomorrow we'll be meeting again at 2 to 4. Isn't it, dear students? Is it fine? And at the end of again in the coming week, definitely I will try to plan one more marathon on the metal cutting. I hope it is clear. Okay, fine. Thank you so much, dear students. Tomorrow, please be there in huge number. Please be there. Okay. So these are the questions we are going to discuss, of course, in the tomorrow session. So dear students, see, this is the Gradeup Super has given you these courses. Gear up, rank up. Okay. So gear up is a very ideal course for the students who want to revise the entire GATE syllabus, dear students. Rank up is a course who the students who are actually they are willing to improve their rank or GATE score. right? And dear students, Vision 2022 is very excellent course for the GATE and ESE 2022. Dear students, right now if you are in second or third year, definitely this will be the very ideal courses for those students. Go through the details of the course, each course. Okay, any query you can contact on the given number. On this number you can, yes, you can contact. These are our star faculties, right? These are our star faculties from the Gradeup. These are our achievers, and this is the subscription pricing. Again, any query you can contact on the given number. So tomorrow, what is date? 23rd of December. Once again, we will be meeting at 2 p.m. okay, which is the marathon session on metal forming. Okay, thank you so much, dear student. Thank you so much. You can follow me on the Gradeup app. You can follow me on the Gradeup app. There are also some of the free series are daily running on daily basis. You can take the advantage from that also, right? Take care. Bye bye. Thank you so much.